Okay. So, now let us instead of doing a 1D formulation, we will jump to a 2D formulation. Okay. It conveys the idea a little bit better. Okay. So, when we look at 2D, again this is common to what we did in the integral equation methods and finite element methods also. How many polarizations are there independent that we can talk about? 2 polarizations, right. So, there are 2 polarizations, TE and TM, transverse electric, transverse magnetic, and any problem, any arbitrary problem can be written as a linear superposition of both of these. So, I can deal with each of these two separately and then worry about superposition later, right. So, TE, as we have said, it consists of which variables? No, Ex, Ey, Hz, right, so far, and Tm was Hx, Hy, Ez. So, let us take the TE polarization. Okay. So, we will just write down our Maxwell's equations once over here. Curl of E is equal to minus mu dB, H. So, given our previous experience with Maxwell's equations, it's tempting to always replace the d by dt by a j omega, but we should remember to not do that. Okay. The whole point of FDTD. Curl of H is equal to epsilon dE by dt, okay, plus j. To keep matters simple for now, we'll assume that there is no current, but we'll add it in later in the module. Okay. Now, in TE polarization, I can I can use these two Maxwell's equations to give me a few scalar equations, right, because the unknowns are only Ex, Ey and Hz. So, the first equation will become, and let us further just take vacuum. Okay. So, epsilon naught, right. So, I am taking the second Maxwell's equation and looking at the x component, okay, and assuming current 0. Okay. So, this is dEx, and on the right hand side I will get a spatial derivative of the H field, and what will that be? You can work it out, right. It won't be Hy, it will be Hz. Then I get the y part of this equation, again time derivative, I will get a minus dHx by d, again this is z x. Okay. So, I have used the first Maxwell's equation, and finally, what is left is the first Maxwell's equation. In that, how many components are there which are non-zero? This equation? Only one, because H vector is only Hz. So, I only have to take the z component. So, I will get the spatial derivatives of E now, right. So, in terms of time derivative, I will have mu naught dHz by dt, and I am left with Ex three equations. There is an extra minus sign where?
Whatever you wrote on the right hand side.
Yeah.
Is just the curl.
Yes.
No, it's minus.
That's correct, right? Yeah. Okay. This is just simple working out the curl now. Here you should not make minus sign, otherwise all your computation is gone for the 6. Okay. So, now we want to, before I sort of lay it out for you, let us try to design this. My variables are Ex, Ey, Hz, that, and they have to be discretized in space and time. Okay. I have seen that the discretization scheme needs me to know E at different points in space, different points in time, right. So, what you, I mean, the way to do this is, you have to make a grid. Obviously, it's a two-dimensional problem. The unknowns are on a grid, right? So, I make a grid. So, this is a repeating grid. I am just showing one unit cell, okay? And what I can do is, I can call this EY. So, at the center of this, okay, and this over here at the center of this I can call EX, and here is where I will do HZ. So, it will become, as we work more with this, it will become clear why I did not define all of these unknowns all at the center of the cell or all at the corner of the cell. I have staggered them out in space. Later on, we will also stagger them in time, but we will come to time first. Right now, we are just dealing with the space grid. So, this grid was what was proposed by Yee in 1966. So, it is also called a Yee cell. Okay. Right. Now, these it's like a lattice, right? So, these points are given some shorthand numbers. So, I will call this the point I comma j, and therefore, this point over here is I plus 1 j plus 1. Okay. So, people also call this a stencil, various names for the same thing. It's a stencil. I repeat it everywhere in space. That's why it's called a stencil.
The grid will end, right?
The grid ends at some point. I mean, let's say it ends on a straight line, right? So then
EY will be there.
only EY will be there. Yeah. So I mean, it ends where it ends, right? So the convention is the electric field is being discretized along the grid boundaries. Okay. Okay, and H at the center. Can you think of a practical reason for doing this? I could have done it the other way also. Huh? Continuity equation. So, most materials that we work with are electric, I mean they are not magnetic materials, they are electric materials. So, we have to many times worry about tangential continuity of electric fields. So, by choosing a variable to be at the grid line, it is easier to work with boundary conditions. So, it is not a golden rule, you can have it the other way, you can define your electric fields to be at the center of the domain and magnetic fields on the boundary. So, this is just one choice. Okay. So, this is the convention. Okay. Now, we also need a notation. So, let us write that out.
So if it was TM polarization, then I would have taken electric field to be this.
I'll show you what we'll do with TM polarization. Okay.
We can have HZ also at each of the grid points.
At the corners, we can have HZ at the corners also. In fact, that's what we do in the case of the TM polarization. Okay. So let's just write down some notation over here. So EX, for example, at I plus half, if I write something like this, EX at I plus half j, you know what that means, right? It means that I am actually evaluating EX at x is equal to x naught, some x naught which is a reference, plus I by 2 times the discretization delta x, and y naught plus j times delta y. So, instead of writing this very long right hand side, I just use this shorthand for the left hand side. I just mention which are the points at which. So, Ex, for example, is not evaluated at integer x's, but it is evaluated at integer y's. So, that is why it is I plus half. Similarly, Ey, where are we discretizing Ey? I comma j plus half, and it is clear what I mean by this. Similarly, when I talk about hz, I am doing I plus half, j plus half. Okay. What about ex? I plus half comma j. Yeah, x naught is some origin, delta x is the discretization, right. So, I plus half. So, I times delta x will bring me to the corner, plus half delta x will bring me to where this electric field is being discretized. It's being discretized in the middle, right, middle of the line. So, that is why the plus half is necessary. Similarly, for in the case of Ey, it's in the y part, it's j plus half, not j.
But when we go in the x direction, there y will be constant.
When we go in the
X direction, but the y coordinates won't change.
yeah, they won't change. So, that is why it's just j. Yeah. I am just trying to discretize a 2D grid in terms of node locations, that is all. Okay. One thing we are missing so far is time. Time has not been indicated over here, and we should discretize time also, right. So, again the notation that we will have for time is, we will put it in the superscript, right. If you see this, it means Ex at some point in space, and t is equal to t naught plus n delta t. Okay. So, we will use these very compact notations to describe where we are talking about space and time. Okay. So, now that we have done this, let us try to convert equations 1, 2, 3 using our central difference idea. Okay. So, the first equation, what do we write for our first equation? So, it is time derivative of Ex. So, for now we will just write, so equation 1, it becomes, so we will just write this as E naught Ex, we will put a dot on top to indicate time derivative. What coordinates in terms of I and j? I plus half j is equal to, now we come to the h part. Okay. So, partial derivative of h z with respect to which coordinate? Y coordinate. Okay. So, what should I write in the right hand side? So, this is h z. Okay, so what should I write this as? Yeah. Yeah. Y, so h of z evaluated at, in terms of I and j, let us try to write it down. I plus half, okay, so h z, I plus half, j plus half, then minus h z, I plus half, j minus half. Is that all? Divided by what? 1, why 1? Delta y. Right, the difference between these 2 points. Do not think that these, I mean only the notation is I j, does not mean that everything is separated by unit distance, right. The separation is there, you can see delta x and delta y is the discretization. I have mentioned it just as a dot on top, we will work it, open it up later. First I want to get the space parts done correctly. Okay. Second equation, again simple. So, it is a time derivative of E y, but evaluated where? Coordinates I, comma j plus half, very good. Now, I have partial derivative of h with respect to x, okay, with a minus sign, never mind the minus sign, h z, first term. Actually, let's absorb the minus sign inside. Okay. Okay, so first term hz I minus half j plus half, not j, minus hz I plus half j plus half divided by delta x. Right. So, there is a sort of trick, a shorthand trick you can use to remember this. The Ex derivative can be thought of as top minus bottom, right, the top value minus the bottom value. So, I write this as top minus bottom, right, and this over here can be thought of as second left minus right. Okay, so just to show you what we have done, we have considered which points so far. We have considered this point, and these are the points that have been involved in these finite differences, right, h z at these points. So, this blue and this red are involved together in giving me E y. This red and this blue over here, they are involved in giving me Ex information, right. Look at the first one, time derivative of Ex, that is I am talking about this guy over here, and what are the values being subtracted? Hz at I plus half j plus half, that is this guy over here, and I plus half j minus half, that is this guy over here, right. So, it is very neat that when I am taking the difference, I am approximating the value at a grid point in between that. That is why I chose my Ex to be discretized over there and not somewhere else. Similarly, second equation you see Ey dot, time derivative of Ey, it is straddled on the left and right, and their difference is giving me this. Yeah, I am taking vacuum. Epsilon naught is here, so it is vacuum. Okay. Then what is left? Equation 3. What becomes of equation 3? So, equation 3, all right. So, left hand side is simple, mu naught hz dot, what are the coordinates? I plus half j plus half, no problem. Okay. Now, I have to write this in terms of space derivatives of Ex and Ey. So, the first term, this is the first term and this is the second term. First term is Ex y derivatives, okay, Ex y derivatives. So, look over here, I am trying to find out approximate Hz derivative over here. So, first term is Ex derivative in space. So, what will the first term be? Yeah, okay. So, Ex I plus half j plus 1 oops, technical problem, this is j plus 1 minus Ex I plus half j divided by delta y. Okay. That is the first term minus, let us write down the second term over here, minus second term is now Ey x derivative, Ey x derivative. So, Ey, what are the grid locations? I, yeah, he is right, this is going to be I plus 1 j plus half minus Ey I j plus half. divided by delta what? X. Right. So once you keep this grid in mind, it's very geometric. You can just see what minus what and so on, right? So now you can appreciate why we have staggered Ex, Ey, Hz in such a way, because all the three equations are giving me an approximation at the correct point. When I take, for example, if you look back here, look at this expression over here. When I take and look at the right hand side is f of z naught plus delta z by 2 minus f of z naught minus delta z by 2. This is accurate estimate of f prime at which point? Z naught. That means the average of the 2 points, right? So that's the reason why this staggered grid is chosen. So when I take the spatial derivative of Ey, right? When I take the spatial derivative of Ey with respect to x, the approximation is valid at the midpoint of those two places, which is where I have chosen Hz to be. So everything is at the midpoint of the other when I start taking finite differences, right? So this is the use of this E cell, right? Ex and Ey are not at the midpoint of the grid, but at the midpoint of the grid line, not in the middle of the cell. Yeah. Correct. So Ex, so remember we have Maxwell's equations which are continuously varying everywhere. We want to solve it numerically, so we are forced to discretize it. So you are saying that I know Ex only at I plus Ex is only known at I plus half comma j. What about Ex at I comma j, for example? You can ask. What would you do? You could discretize it. There are two ways. So if I want Ex at ij, I can discretize it at half the grid size, so I will get at that point also. Or the smarter way would be average. I know Ex on the left hand side, I know Ex on the other side, right? So if I take the average of those two, I will get an approximate value of the electric field at I comma j. So, and remember these delta x and delta y, they are in your hands. You choose how fine you want to discretize it.
What about the
Direction of
the Ex and Ey?
these are
So we don't have a direction.
there is no direction. I mean, I'm assuming it's along a line. So Ex, whatever, supposing you get a value of 5, then I say okay, it's along the plus x axis a value of 5. If you get minus, then it's pointing in the opposite direction. So it's a scalar, it's not a vector, because Ex is a scalar, right? So the x component of E is a scalar, can either point in the plus x or the minus x direction.
So if I want to tell value E at a point,
Yes.
so should look at Ey and Ex at that point.
Yes, so supposing you want to find out, so good question, I want to find out what is the value of the electric field at I comma j vector, then what will you do? Average the x components, average that's the x part of your electric field, average the y components, that's the y part of your field, net you've got a vector.
Average as in look at the points next to it, right?
Yeah. So for example, let's say that here I'm asking what is electric field over here, that is the question.
Somewhere that grid.
Somewhere
In that grid.
you want somewhere inside the grid. Yeah, so if I want to find the electric field at this vector over here, so I will take the x component to be the average of this Ex and this Ex, right? So that will give me the x part.
So then there will be points where we can't do anything.
Yeah, there will be points. So let's come to it step by step. So at this grid point, what do? I take the average of this and this. There's also a Ey here and a Ey here. I take the average of this, and that pops in over here into the second component, right? So this goes into the first component. Now I've got a vector E. I can repeat this at every grid point. Easiest thing. So basically, what I've done is on a square grid, on a rectangular grid, I have got at every node location, I have got the electric field. Now you want even finer than that? Then there are two things you could do.
But not just to the node location.
Yeah, you want somewhere inside the cell, right?
In the middle also we can talk, right?
Yeah, you want to know now what is electric field, let's say at the location of Hz you want to know.
Again we can average.
That also you can average.
But any other other point itself.
At any other point. So what would you do? So what is that mathematical procedure called? You all know it. All of you know what. So you want to find out, the question is find out the electric field at some random point inside here like this. What is that word? Technical word, you all know it. Interpolation. Right? Once you know values on a grid, if you want finer than that, interpolate. Okay. Now typically this turns out to not be a real issue. I mean, because you're seeing it for the first time, this question comes out. The discretizations delta x and delta y, typically they are so small, they are on the order of lambda by 10, lambda by 20, where wavelength is lambda, right. So for example, if I have a 1 gigahertz, your mobile phone works at 1 gigahertz, 30 centimeters, so your discretization is 30 centimeters say by 10, 3 centimeters, or even smaller than that, let's say 1 centimeter. So every 1 centimeter you are anyway calculating the electric field. It doesn't vary so much that you want to know at some very minute location. Okay. This is also, it will turn out to be quite a disadvantage of these finite difference time domain methods, because you have to discretize everything so finely. So that's why these are called brute force methods. You just brute force in space and time calculate everything, even though you don't need it. Finally you don't need it, right. The radar cross section example, finally what do I want to know? I want to know the tangential currents so that I can apply Huygens principle to find out the field everywhere. But when you do FDTD, I have to find out the fields everywhere in space. From that only take out what is along the edges. So there's a lot of work that needs to be done to just get one small thing. What about the time derivative? Yeah, so that is what we will talk about in the next slide. How do you deal with the time derivative? Okay. All right. So hopefully everyone has got this stencil very clearly in their minds, right. So main point is staggered by half a grid.
Delta x go like this.
Yeah, go like this, right. So top minus bottom, left minus right. These are the keywords. All right.